Good afternoon, everyone. I trust you have had a good day you're having a good day so far. Welcome to Networks 2. This will be a rather short lecture. The topic is quite simple, and so we will get through in less than the scheduled 2 hours. However, we'll see if there are things that need to be clarified. We will do so. All right, so let's get started. I trust your preparation for Friday has been going well. Um, so let's get cracking. All right, so today we're going to be looking at resonance due to harmonics. All right, resonance due to harmonics. And most persons would have done harmonics or based on the topic from Networks 1, would have been complex waves. All right, and in that topic, we mentioned harmonics. Okay, so we're just going to be looking briefly at resonance as a result of harmonics. So let's quickly, a brief review. What we have here before us, a triangular wave, periodic time, big T. Similarly, we can have, in this case, well, it's not really a square wave, this would be a rectangular wave. Again, having a periodic time T. And for each of these waveforms, we can describe them mathematically as f of t equal to f of t plus t. That's for our values of t where t, big T that is a positive number. And what this is really saying here, what this is really saying is that the function f of t is repeated every t seconds, which is where we get our periodic time. So for every t seconds, right, we have the waveform, which in this case would be this, being repeated. So we have it repeated for another t. It's repeated here. Right? So that would be big T. That would be big T. For every big T, the waveform is repeated. That's what we are saying. Right. And of course, we know that big T is the interval between two successive waves. And we refer to that as the periodic time. Also, I know this is a review, so I may be going a little quickly, I know, but you would have had these notes already. All right. Of course, in terms of describing our complex waves or the components of the non-sinusoidal wave, we refer to that one major component, which is a large amplitude sine wave, and it has the same frequency as a periodic wave. We refer to that as the fundamental. So this large waveform here, the sine wave here, That's our fundamental. Of course, the blue is the blue waveform. That would be our complex wave. So this is our complex wave. All right. We are saying that within that complex wave, you have that fundamental. That's the same frequency as the complex wave, because of course the periodic time, all right, will be the same. And we know that the frequency is equal to 1 over t. All right. All right, so we have our fundamental, and then of course, along with our fundamental, we have other component sine waves. With frequencies which are exact multiples of the fundamental. So we have the exact multiples, which will be 2, 3, 4, etc. All right. And we refer to these as our harmonics. And the harmonics are numbered according to the ratio of their frequency to that of the fundamental. So in terms of what we have here, I'm just breaking down our complex wave. Again, here's our complex wave. So that's our complex wave. And we're saying that these other waveforms, now outside of the fundamental, these other waveforms are exact multiples, or have frequencies which are exact multiples of the fundamental. So in brown, here we have one wave, here we have another, and we have another, okay? So it means therefore that we would have had 3 complete waves, all right? So we have 3 complete waves of this waveform, right? Which means therefore that for that waveform, it will be 1/3, or its periodic time will be 1/3 of t. Yes. T, of course, being the periodic time of the fundamental. Okay, 1/3 of t. And since we had said that f was equal to 1 over t, if this wave has a periodic time which is 1/3 of t, then it means therefore that the frequency would be 3 times. All right? Because it would be 1 over a third t, which would give us 3f. So we have 3 of these waves. We have 3 of these waves within the same time period of the fundamental. So it means that this would be, and we speak of the, or we count the harmonics ordinately. So it means that this would be our 3rd harmonic. If we consider the bluish green, we would have here 1. We would have 1, 2, 3, 4, 5. All right, so we'd have 5 complete waveforms within the same period of the fundamental. So that means the frequency will be 5 times the fundamental. So that would be our 5th harmonic. And then, of course, the blue may not be that easy to count just looking on what we have here. but I'm telling you that it is 7. So that would be our 7th harmonic. Okay. So for this particular complex wave, which is in the process of development, I can, for those who may not have covered this topic prior, ultimately this will work out to be a square wave. All right. So we'll have a square wave here. All right. Let's remove all of that. And as we add harmonics, you'll find that the number of ripples in the top of the waveform will increase until ultimately it flattens out. So that's a square wave. So in essence, what we're showing here is that your square wave has odd harmonics. So it has the third, it has fifth, seventh, ninth, 11th, etc. All right. So that's for your square wave. All right. Now, for a complex voltage, and you may just want to take this, you want to write this. So for a complex wave, V, which is V1 m sine omega t, V2 m sine 2 omega t, plus V3 m sine 3 omega t, supplying a circuit which consists of a combination of passive elements, whatever those elements are. All right? For that complex voltage, it will produce a corresponding current as shown. And the coefficients for each of the currents, so I1, M, I2M, I3M. These are just amplitudes. These are given by V1M, over Z1. So I1M would be the amplitude when we consider just the fundamental. I2M when we consider the second harmonic alone. And I3M for the third harmonic. Anybody have that?
Yes, sir.
Okay. So, this is, as I said, just a brief review. Having said all of this, where do we go from here in terms of the resonance? So, a couple of points I want to make. Right? The possibility of resonance occurring, given the typical values of inductance and capacitance used in industry, is highly unlikely. And recall that resonance is going to occur, at least for the series circuit, when the net reactance is zero. So what we're saying, given the values the values of inductance and capacitance that we're going to be exposed to from an industrial standpoint, resonance is highly unlikely. No, I said unlikely, I didn't say impossible. All right. The second point we want to note is that for a voltage input that is not purely sinusoidal, there's a possibility of resonance occurring at or near one of the harmonics. So whilst for the your standard operating frequency of your 50 and 60 hertz, you may not, and in addition to the values of L and C that we are going to be using, you will not be seeing, or it's highly unlikely that you'll see resonance occurring. The fact is, when we are looking at non-sinusoidal input, all right, so where there is non-sinusoidal input, the possibility of resonance now increases when we start to consider the harmonics, because the harmonics, depending on the waveform, and if you go back to the basis of our harmonics, which is your when you do our analysis, it's to infinity. The reality is, most of our analysis only considers the harmonics whose amplitude are significant. So when I looked at the square wave here, yes, we were only considering up to the seventh harmonic, but of course that goes to infinity. Yes, so there will be harmonics that have small amplitudes, yes? And based on what we have here, we see that the amplitude would also vary, because if we're dealing with capacitance, as we increase the frequency, the capacitive reactance will be falling, and so the possibility of the amplitude, the current amplitude is increasing would also, or the possibility of those increasing would also increase. But at the same time, we know that the inductance would also be increasing. So the capacitance is falling, decreasing. The inductive reactance is increasing. So, we can't make any definitive statements as to what or at what point resonance may occur. What we know is that it can occur at a frequency beyond system frequency. All right? So that is something we want to make note of. And the third point is that if resonance occurs, yes, at one of these harmonics, then the amplitude of the affected current can be very high, can be quite significant, and that is something that we know, generally speaking, with resonance. So we know for series resonance that the current is at a maximum, yes, at resonance. So parallel resonance, it's a minimum. The current is a minimum entering the circuit, but of course, the current within the circuit can be much larger than what is entering. So the fact, what we're trying to highlight here is that Yes, you may not see it at system frequency, but based on harmonics, depending on the type of input that you have to your circuit, resonance can be experienced um, in your system. And there are certain operations where resonance at all frequency is a possibility. Yeah. Capacitor start, induction motors, that possibility exists. Um, where you have large, well, it's not as great an issue today with the new technology for our computers, but in time past, where you had large numbers of computers, you then be creating capacitive loads or high capacitive loads on the system, and so that can cause some issues, and which has to be considered from a poor quality standpoint. But that's not our focus this afternoon, this evening. So we can have increased magnitude in terms of occurrence. And then finally, um, where this occurs, yes, we said that the circuit have what we refer to as selective or harmonic resonance. So it's not occurring at system frequency. And system frequency or pole frequency, as I mentioned before, would be the frequency, um, your standard supply frequency, which is your 50 or your 60 hertz. But it can occur at multiples of these frequencies, which we refer to as harmonics. All right. Okay, so let's just get down to what we already know. So for this circuit, take the circuit for me. For this circuit, we know that the condition for resonance at the fundamental, so at the system frequency meaning the frequency of our supply. Right? So at system frequency, that's the condition for resonance. I lost connection just now. Sorry about that. Let's get back to where we were. All right. So resonance at the fifth harmonic would be given by.
We could go back to the previous slide there.
So at the fundamental, L is equal to 1 over omega C.
Thank you.
All right. At the fifth harmonic, Because remember that the condition for resonance, at least series resonance, is that the net reactance will be zero. So, and the reactance is a function of frequency, yes? So 5 omega L will be equal to 1 over 5 omega C. That's at the fifth harmonic. So we can give a general expression, right? That resonance, if resonance occurs at the nth harmonic, then n omega L is equal to 1 over n omega C. All right? And surprise, surprise. That's it for resonance due to harmonics. But of course, let us do a couple questions just to make sure we understand what is being done here. All right? So take this question from it, please. All right. So we have our series circuit. We have the supply voltage, the resistance. We have RL and C, and we want to determine the fundamental frequency for resonance with the third harmonic. All right, so I think we all know this by now. We have our circuit. It is being supplied by V. 0.5 henries, 20 ohms. 20 ohms and 0.2 microfarads. All right. And but of course, I'm not putting in a sign
Excuse me, sir.
source because the waveform is obviously not sinusoidal. Right? So it's a complex wave. And we want to determine the fundamental frequency given that resonance occurs at the third harmonic. So we know that based on what we just indicated, that general formula, we know that n omega L is equal to 1 over n omega C. Okay? And quite frankly, it doesn't matter if you said n omega C equal 1 over n omega L. All right? You get the same result. Anyway, so since it's occurring at the third harmonic, what we know therefore is that 3 omega L is equal to 1 over 3 omega C. All right, or omega squared is equal to 1 over 9 LC, which implies that omega is equal to the square root of 9 LC. And we are interested in finding F. So F is equal to 1 over 2 pi square root of 1 over 9 LC. All right. So work this out for me, please.
Sir, 167.76 hertz.
Go again.
167.76 hertz.
What's happening here? All right, it's 167.7 hertz. All right. Thank you, Mr. Blackwood. All right. So that's our frequency. We're then asked to determine the maximum value of the current. So what the amplitudes, the current amplitudes at the fundamental and at the third harmonic. Now what we are told, and you know, That's part of the reason we went through the little review, because we know that the fundamental is that large amplitude waveform. It usually have the largest amplitude, and based on what we have here, for the fundamental, the amplitude here is 400, and for the third harmonic, it is 10. So there's a 4,000% difference. Eh? Okay, now let's start with the fundamental. We can say that at the fundamental, we know that I1M is equal to V1M over Z1, yeah? We know that to be true. So I want you to now calculate Z1, where of course Z1 be R squared plus X squared, all right? X, of course, being equal to XL minus XC. And this is occurring at the fundamental, all right? So calculate that for me quickly. So find Z1. Got it? Z1?
Is it 2 minus J?
Pardon?
2 minus J 4216.37.
All right, so give me we want the magnitude, so let's give me the final magnitude. We're asked to find the magnitude, so give me the magnitude of Z.
4216.37.
So is it that the 2 does not affect it?
Calculate, and that's what I got.
All right. So I1M is therefore equal to 400 over 4217. Okay? Approximately equal to 0.95. 0.95, sorry. So this is the amplitude, the current, the amplitude of the current at the fundamental. All right? But the question asks us to also determine the amplitude at the third harmonic. So quick question. what would X be equal to at the third harmonic?
Zero, sir.
Be equal to 0. So therefore Z3, right? So at the third harmonic, Z3 would be equal to 2 plus J0. Right? Since XL3 is equal to XC3. All right? Which implies, therefore, that I3M is equal to 10 over 2, which is equal to 5 amperes. And what this example is highlighting is the fact that although the fundamental had the fundamental for the voltage was all of 400 volts, yes, and for the third harmonic was only 10 volts. That corresponding current for the fundamental was less than 0.1 of an amp, while for the third harmonic, we had 5 amperes. So because resonance occurred at the third harmonic, we are seeing 50 times the current. At that harmonic. All right. Any questions?
Yes, sir. Sir, at the fundamentals, sir. To calculate XC and XL, would it be the frequency that we found earlier, as in the 167.76?
Yes.
Okay. Because I was doing something wrong. I thought it as in it was at the third harmonic that frequency was, so it would have been 1/3 the value.
Oh, okay. No.
Okay.
All right. Good question, actually. All right. Any other question? Okay. So take this from me quickly. All right. But I have answers on it. It's pretty similar to what we just did. All right. This is and the volunteers. Okay then. All right. So we will. As I said, it's quite similar to what we just did. I'm assuming the lack of volunteer mean that you're as comfortable with this. So I'll just leave you to do this one on your own. But really, that's it. That's all that I have to say on this particular topic. I did say it was rather simple, and so it's usually there as one of those guarantee or those one of those questions that guarantees you a mark. All right. All right. There be no questions. I will just take the register, and that will be it for today.
Sir. Sir, I have a question about the previous question.
Pardon me?
I have a query about the previous question.
I can't hear you clearly. Then.
Saying I have a query about the previous question.
Uh-huh.
Why was XL 0?
You mean here?
Yes, sir.
This isn't XL. This is XL minus XE. Yeah?
Yeah, okay, I got that part, but why wasn't quite sure why the value was 0.
Because this is true. The basis on which we found F was because of this. But tell you what, let us not take the easy route. What I want you to do for me, you have this as the fundamental frequency, all right? You're comfortable with how we got that?
Yes, sir.
All right. What I want you to do is to calculate based on the capacitance and inductance values you got. All right. I want you to calculate XL and XC at the third harmonic. Just calculate that for me quickly. Or I could give you another exercise. Did you do the calculations for over here at the fundamental? Did you get the 4217?
Yes, sir. I got that value.
Okay, what did you get for XL?
527.03.
527.
Yes, sir.
Okay. And what did you get for XC? Hmm? What did you get for XC?
4,743.53.
Okay. So I want you to 4,007 what?
4,743.53.
Okay. All right. Now, I want you to multiply this by 3 and divide this by 3.
So divide XC by 3.
Yeah, man. And multiply XL by 3.
You get the same value.
So it means that at the third harmonic, both are equal, eh? Because if you increase the frequency, the capacitive reactance falls. You agree?
Yes, sir.
Uh-huh. And if you increase the frequency, the inductive reactance will increase. Yes?
Right.
Okay. So when we do that, you triplet, so you multiply this by 3. You triplet, so you divide this by 3. You see it now?
Yes, sir.
Huh?
Yeah, I see it.
All right, cool.
Sir,
Yeah.
so Z1 equal root R square plus X square, right?
Uh-huh.
So, but for XL minus XC, I got the 4,218. So that means that when you put it back in the R square plus X square root that, you're supposed to get something different, right?
Not sure following it. You got these values for XC and XL?
Yes, sir.
All right. When you subtract them, what you get?
When I subtract them, I got 4,218.
4218.
Yes, sir.
But based on what I'm seeing here, this is 7. That's 3. Oh, you're going to get 8 out of
No,
that.
because for XC, I got 4,745.
So like you're round off something there then. That's just a rounding error.
So that means that Z1 would be still 4,218, even though that's just XL minus XC. That would be just the X part and not the R, the root R
R
square.
is 2. R is
Okay.
2. So if you were to add 4 to whatever you got as the square, when you find the square root, it will be hardly different.
Okay.
All right. So let's just deal with the register and then we wrap up for today. Adams. Is Adams not there? Okay, Bart. Is Bart not around? Blackwood.
Present, sir.
Brown, Beresford. Okay, Miss Brian. Beresford. Also. You have a question on support, huh? Sabuso. Campbell.
Here, sir.
Chen.
Here, sir.
Sir,
Clark.
yeah.
Clark.
Yeah, Marcelo Clark here, sir.
Crosdale.
Yes, sir.
Darby. So Darby gone. All right, Davis. Donna.
Yes, sir.
Ellis. Ferran. Forrester. Grant.
Yes, sir.
Gray.
Here, sir.
Jeffrey, Kyle. Okay. Johnson Antonio.
Here, sir.
Kenyatta. Kamika.
Here, sir.
Lewis Nicholas.
Here, sir.
Lynch.
Yes, sir. I'm here.
McFarlane.
Here, sir.
Merritt.
Here, sir.
Merritt.
Here,
Oh,
sir.
okay. Montague.
Here, sir.
Nevers. Phillips.
Here, sir.
Porter. Yeah. Just heard you. Ramsey.
Here, sir.
Reddy.
Yes, sir.
Thomas Vanai.
Here, sir.
And Watson.
Here, sir.
All right. Thank you. All right. I just want to encourage you all for Friday. Please, just ensure that you are doing your own work. I trust by now those persons who are using the system for the first time or this approach for the first time before last, that they now understand what to do. Remember, if you have not completed the analysis, please do not make a selection. Yes, I know it's a multiple choice, but you're penalized for incorrect answer. All right, so the guessing thing, just avoid it. There's absolutely nothing on the paper that you have not done already. Therefore, there's nothing for you to be worried about. I know it's technically an open book test, but if you're not familiar with the material, then you're gonna have challenges. Yeah, that's all I'll say for now. I wish you all the best. Please, although we're at home and it may be a little more relaxing, I do encourage you to get quality rest before you do this exam. All right, this is 25% of your module grade, so it's an important assessment. All right. So if there are no questions, that's it from me for today. We will start our new topic on Monday, all things being equal. I will send to you the assignments for your project. All right. And we'll take it from there.
Sir, I have a question, sir.
Yes.
Right. So being that we send the rough work, right? So the rough work is not used for anything otherwise from just the proof. You don't use it to allot marks or anything of the sort. Adjust the multiple choice.
It is for validation.
Repeat.
It is for validation.
Okay, so you don't allot no marks at all. Adjust the multiple choice alone, basically give you the marks. Basically.
Computer marks the exam. I've already explained one of the reasons for this is that we are doing 4 assessments in a very short period, and it's important that you have that feedback. All right, so I use what you upload to validate and to ensure that you have done the work. Because at the end of the day, it is important that the credibility of the degree that you're awarded after the 4 years, whether we're online or otherwise, that the credibility of the degree is maintained. It can stand up to scrutiny. We're not just doing something, off the cuff and to satisfy ourselves. We have to ensure that the work completed by everyone doing all these modules during this time using this method is credible. All right?
And nothing, sir. But for example, right? Just for like the 2-port question, right? May I say like if you make a mistake for like even one of the parameters or a number in the parameters, it means a whole question wrong, sir. Basically, you lose everything, you know.
So Merit, you may not be aware, but based on how the exam is set, it asks you questions based on the various stages in the question.
Understandable, sir.
Good. So I am not only testing you for one answer at the end, it is testing you at different stages. And you can gain marks for those early stages. All right. So whether I'm looking at what you have uploaded as, and you call it rough work, but I wouldn't really call it that. And I hope that what you upload does not resemble rough work. Enough said on that. Anyway, whether or not it is being assessed using the selections that you made, or me sitting down with a pen and marking it, it amounts to the same thing, because I would have been assessing the thing or your solution based on the stage at which you have that.
All right,
As a matter of fact, it may be of greater benefit to you. At least you don't have to draw some circuits. But anyway.
Just to add, sir, the ABC, just to add on a little clarity, the ABC throughout whatever alphabet, that is just it's showing a sequential order, order of responses to be selected.
It's not.
It's not.
What you have, all the answers to the questions that you're asked are in that list. So if you have 4 sections,
okay,
the 4 correct answers are in that 16.
Okay.
So it is important. That's why I keep stressing it is important that you are not focusing on doing a multiple choice exam. The multiple choice is just a means, a mechanism by which we can quickly evaluate your work.
Okay.
But the real focus is you taking pen, paper, and work it out as if you are sitting in an exam room. And I can't emphasize that any stronger. Right? And I am also using it to the approach to address the issues of collaboration and that type of thing. And I'm using collaboration as a nice word.
Right? Understood, sir. I appreciate it.
And I am stressing with even greater vigor this evening that come Friday, I am begging you, do your own work. I will not expand on that, but I'm saying do your own work. It will be a very painful exercise if you did otherwise. All right, so just focus on your own work. Do it. Once you have gotten it correct, the answer is there. You make your selection. If you made an error with your selection, you have the option to go back, change it, correct it. But it must be aligned with the work that you upload to me. All right?
Understood.
Okay. I hope I have answered all the questions. All right, then. So have a good evening, everyone.
Yes.
So I want to ask you a question about something you got for questions. Who did that saw? It's a transient question.
I'm listening.
Okay, sir. So at one point, sir, I saw the question was the system was underdamped, so it had sine and cos in the solute transformation. I saw your transpose, and you had like tan 3000 t is equal to 3 on one side, but going down from there, I see how 3000 t is equal to 1.249.
Yes.
Sir, I am not sure how you move from the tan 3000 t to the 1.249, sir.
Well, obviously, I wouldn't be able to tell you just based on you saying it to me. However,
Sure.
Something like that sounds as if you were trying to determine the time at which maximum occurred.
Yes.
Maximum, okay.
Sir.
Maximum displacement, yeah?
Sure.
If that is the case, then what to get to the tan, yes?
Yes, sir.
You would have had an expression in sine and cos.
Oh, yes.
And so when you divide them, right, you'll get the tan.
Yes, sir.
So in doing that, so you'd have sine whatever, A sine, and I'm just gonna group everything and call it R. So A sine R is equal to B cos Y. So if you're dividing those two, then you'll get tan of the angle, yes, is equal to a constant. So you'll be finding the inverse tan. Now, of course, what we have, and I hope I would have said it, or even if I didn't. The angles that we'll be dealing with here would be in radians.
Okay.
So the inverse tan there would be based on tan based on the angle in radians, not degrees.
Sure. That's the problem, sir. It has, if you work it in degrees, you'll get something else. But if you work it in rods, you'll get your answer.
Yes. So it's
So all the time it's rods. Okay.
It's always in radians.
Okay, sir. I got the answer. I got the answer now, sir. And I understand how you got the 1.249, sir.
No problem.
Thank you very much.
You're most welcome. Well, I suppose the question benefited everybody. So now you know that you only deal with radians. All right. Okay, folks. So have a good one.
Yes, sir. Same to you.
Same to you.
Same to you.
Cheers.
Yes, sir.